Okay, so the idea is Q1 plus Q2 is equal to 0. If Q1, we call that the iron, then that's going to be 0.1 kilograms times 450 times T final minus the initial temperature of the iron, which is 5 degrees Celsius, plus the mass of the water times its specific heat, 4186, times temperature final minus the initial temperature of the water is equal to 0. So anybody know why I'm using, so normally when we have temperatures at a specific instant, we convert any Celsius temperatures or Fahrenheit temperatures to Kelvin. Why is it okay for me to use Celsius temperatures here? I mean, I could have converted it. What? Yeah, it's because it's a difference. It's because this appears as a final minus an initial. Okay, so if you multiply this through, you get, what's that? 45 TF minus, what's 45 times 5? 225. And then, what's that? 2093 TF minus, what's this one?
41.
Oh yeah, 41860 is equal to 0. Then combine the T's, and what do you get for TF? 19.68 degrees Celsius. Okay, and there are two reasons that that final temperature is so close to the initial temperature of the water and relatively so far from the initial temperature of the iron. What's one of the reasons? Yeah, the masses are different. There's more water than iron. But it would be closer to the water, the initial water temperature, even if it had been the same amount of mass of each of them. And why would that be? What's the other thing that determines? Yeah, so water has a higher specific heat than iron does by, a factor of 10 almost. And so the higher the specific heat, the more energy has to be, added or removed from an object to change its temperature. And so you're taking a lot of energy from the iron, or you're adding a lot of energy to the iron in order to change the temperature of the water. Okay, so now with phase change, it's still based on conservation of energy. So we're still going to have Q1 plus Q2 is equal to 0. But now we're just going to have to do it in multiple steps. Where each step ends at either a phase boundary of one of the materials or the entire amount of one material completing its phase change. Okay, so here's an example. Say that we have 0.02 kilograms of ice starting at 0 degrees Celsius, put into an insulated cup of water, liquid water. Let's say we have 0.4 kilograms of it. That's initially, again, at 20 degrees Celsius. 20 degrees Celsius is about room temperature. That's why that keeps coming up. And the question is, what's the equilibrium phase and temperature? Okay, so I guess first let me give you the specific heat for ice is 2100 joules per kilogram Kelvin. The specific heat for liquid water is 4186 joules per kilogram Kelvin. So if we're starting out with all of this 0.2 kilograms of ice, you know, it's all starting out as a solid. What's the first? So first, which way is energy going to go? Is energy going to go from the ice to the liquid or from liquid to the ice? It's always going to go from the high temperature to the low temperature, so it's going to go to the ice. And the energy being added to the ice, what's it going to do? What's the first bit of energy going to do that's added from the liquid to the ice? It's going to change the phase. So every bit of energy we add for a while is just going to turn that ice into liquid at 0 degrees Celsius. And what's removing that energy, you know, that energy has to come from somewhere. So what's removing that energy going to do to the liquid? It's going to lower its temperature, right? Because it's not at a phase change boundary, right? So, so the first step of this process is we're going to do a calorimetry, set up a calorimetry equation where the heat added to the ice is represented by the latent heat, and the heat removed from the liquid is represented by the specific heat. Okay, so step one. The ice is going to liquid and the liquid's temperature is going down. We're still going to think of this as Q1 plus Q2 is equal to 0. But the form that that's going to take is the mass of the ice times the latent heat of fusion for water. So that's representing the energy that's going to the ice, and the energy that's leaving the water is the mass of the liquid times the specific heat of liquid water times the change in temperature. So I'll write this as T2 minus T1. This L fusion for water, that's just something you look up, and that's 333,000 joules per Kelvin. Okay, so this equation becomes 0.02 times 333,000 plus 0.4 times 4186 times T2 minus 20. So you end up with 6660 plus 0.4 times 4186 T2 minus 8 times 4186, and you get, solve for T2, and you get the T2 is equal to 16.02 degrees Celsius. Okay. So at the end of step 1, the liquid formerly known as ice is all at 0 degrees Celsius. And the liquid is at 16.02 degrees Celsius. Okay, well now they're all liquid. But we have to keep track of, we're going to think of it as a pocket that started out as the ice and a pocket that started out as the liquid. Okay, so now what's going to happen for step 2? Which way is energy going to flow? So we still have, even though they're both liquid, we have that smaller pocket of liquid that's at a lower temperature. So energy is going to flow from that bigger pocket to that smaller pocket. Now they're all liquid, so there's not going to be any more phase change. And so step 2, we're just going to do now calorimetry without phase change to find the final temperature. So the idea is we're going to, again, think of it as Q1 plus Q2 is equal to 0. How are we going to represent Q1 and Q2 now? We're done with the phase change, so we're not going to use the latent heat. We're going to use the specific heat. And now, one more thing I just want you to be conscious of. Say that Q1 is the heat added to that stuff that used to be ice. What specific heat are we going to use? Are we going to use the specific heat for ice, or are we going to use the specific heat for liquid? Yeah, we're going to use the specific heat for liquid. That's something that people get wrong a lot of times because they're like, well, it started out at maybe like ice is somehow its identity, even though it's a liquid, you know. It started out as ice, so maybe I'll use that one. But think of it this way, like every bit of ice and every bit of liquid at some time in the age of the universe has been each of those two. Okay, you know, any liquid water has been ice at some point during the ice age or whatever. And every bit of liquid, every bit of ice has been liquid at some point. So you can't go based on what it used to be. It's just determined by what the phase is at the instant that you're dealing with. So yeah, these are both going to be 4186, the specific heat of liquid. So we have the mass of the small pocket that used to be ice times 4186 times T final minus, what was the initial temperature at the start of this phase? At the start of this step, I mean? 0, yep. And then 0.4 times 4186 times T final minus, what was the temperature of the big pocket of water? Yep, 16.02 is equal to 0. And if you multiply all this out, go through all the algebra, you get that the final temperature is equal to 15.26 degrees Celsius. Any questions about that? Okay, one thing to notice, this is sort of a like loose statement, but it's kind of an intuitive statement. But latent heats are big. It takes a lot of energy generally speaking, to change a material's phase. And that fact is used in a lot of engineering applications. So that fact is, I'll say, exploited in many engineering applications. Refrigeration, air conditioning, heating, the idea is if you have if you want to exchange a large amount of energy, a large amount of heat between two materials, which is what you're trying to do in all of these cases, put one at its phase change boundary, and the other one, which is a different material that doesn't have the same phase change boundary, at a nearby temperature. So if you have this blob of material and this blob of material, this one is at the phase change temperature, and say that you want to take energy out of this. This one is, say, plus 1 degree Celsius, like basically the same temperature. Well, if you think of this as, ice at 0 degrees Celsius, even though these aren't at a very different temperature, energy is just going to keep pouring from this one into this one. Okay? And the bigger you make this, the more energy you can get to pour in here. And then, so later you can use that energy to increase the temperature. And, you know, I'm not going to go into the details of how you do it, but it takes advantage of the fact that, so what would happen if you weren't at a phase change temperature? What would happen if you had this at, this wasn't water, it wasn't at its phase change boundary, and you had a 1 degree temperature difference? Well, a little energy would go in, these two would be at the same temperature then, and that would be it, you know? But since you're at this phase change boundary, energy just keeps pouring in there as the material changes phase, and you can take advantage of the fact that you've gotten all this transfer of energy. Okay, well, any questions about any of that? You know when you put like hot coffee or hot water or something into a travel mug, and then the first sip you take, there's like an explosion of air, like air rushes out. You know why that is? Because inside your travel mug, it's insulated. It's basically like a calorimetry thing with a small amount of air that's in there and a big amount of hot water, you know. And so that hot water and the air inside are reaching an equilibrium temperature that's hotter than the air. And so that air temperature increases, right? And you could do that calculation. And what happens according to the ideal gas law if you keep the volume the same and increase the temperature? You keep the number of moles the same, increase the temperature, the pressure goes up. And so when you open the opening, there's a higher pressure inside, shoots out to equalize.
Do you have an example that you can give about the energy change and the phase change order?
For phase change? Yes, well, I can tell you sort of how air conditioning or refrigeration works. So essentially, refrigeration works like this. You have a gas called the refrigerant. That's moving around a path. And on one part of the path is the cool, let's call this the cool area. That's the part you're trying to take energy out of to cool down. And over here is the warm area. This is the room, okay? And you have your refrigerant moving around a cycle like this, okay? And what you're trying to do, here's the hard thing about this, is you're trying to get this refrigerant to pull energy out of the cool area and then reject energy to the warm area. Well, that sort of goes against the way calorimetry works, right? So that takes a little bit of doing. But what you do is this refrigerant is, let's see, it has a phase boundary that's near room temperature. Okay. Or let's say, actually, it's more useful if the phase boundary is near the cool temperature. Okay, so it comes in here. When it gets here, it is liquid. Okay. It's liquid that is slightly cooler than the cool area. Okay?
And right on the edge of its phase boundary.
Right. It comes here. Since it's a slightly lower temperature than the cool area, heat pours out of the cool area into it, turning it into a vapor. And it's still at the same temperature. Now there's one more trick you have to do, because somehow you have to get this gas, this vapor, to a higher temperature than the warm temperature. Can you imagine how you do that? What? Well, you want it to, that wouldn't do you any good. You could do it that way, but it wouldn't do you any good because you want it to be rejected out to this air. You don't want it rejected to air in your, so what you do is you compress it. You put a, you know, put it under a lot of pressure. That increases the temperature. Now that same gas drops heat off out in the room. So here you increase the pressure. Up here you decrease the pressure. It drops back down into a liquid that's again cooler than the cool area, and it goes around and around that way. Now you could do this exact same cycle without a phase change. The problem is it wouldn't be very efficient, because the step here where this liquid is slightly cooler than the cool area, you get a small amount of heat going from the cool area to the refrigerant, and then they'd be at an equilibrium temperature. You wouldn't get any more transfer, and so it would be vastly, you know, slower, and you'd have to worry a lot more about inefficiencies. This way, because of the phase change, heat just keeps on pouring from the cool area to the refrigerant until it's entirely changed phase, and then you go around. So that's an example. Any questions about, I mean, that's not something you have to remember. That's the kind of stuff you talk about in like engineering thermodynamics classes, but it probably, even though in theory you could do this without phase change, inefficiencies in, you know, the insulation and stuff like that would probably make it nearly impossible to get air conditioning or refrigeration to work without that phase change effect. Any other questions about any of this? Okay. So how do you get heat to transfer? So far, we've said, so heat is exchanged from a high temperature material to a low temperature material. But how? How is it exchanged? And there are three ways. So three methods for heat transfer. Um, as illustrated by the transfer of heat from a hot frying pan to a human tongue. Okay, so the first way is conduction. So here's the frying pan on the burner. And the burner heats up this part of the frying pan, right? I mean, the part that's touching the flame or whatever is right here. So, you know, what does your experience say about licking the handle? That's not a good idea, you know? And the reason that's not a good idea is that this energy conducts from this material to the adjacent material to the adjacent material. In conduction, the molecules don't change location. But their energy is transferred from one to the next to the next. Okay. The second way that heat is transferred is convection. So with convection, ooh, his tongue got a lot bigger. Maybe it's a different guy. You don't wait for one molecule to heat up the next molecule to heat up the next molecule. You just pick up the pan and move the hot part over to your tongue. Okay? So in convection, the high temperature molecules actually just change location. So examples of convection are, well, convection ovens. Do you know what happens in a convection oven? It just moves the air around inside a convection oven, so you don't get, because the problem is you put your frozen enchiladas in the middle of an oven. Out at the boundary of the oven, like near the walls, it might be 450 degrees, like it says on your dial. But near your frozen enchiladas have cooled off the air. And so they're not actually at 450 degrees. And so what you want is when energy goes from, a lot of energy goes from the local air of the oven to the enchiladas or chimichangas or whatever you prefer, then the motion of the air gets that cold air, cooler air, out to a different part of the oven where it can heat up and moves hot air over to your food. Another example of convection is wind chill. The way wind chill works is, if there's no wind, you're constantly heating up the air right around you, and that keeps you warmer than if the wind keeps moving new cold air to your skin. And then if any of you have ever had the horrible, Eric, I'll bet you've had an ice bath at some point or another in your life. If you've ever had the horrible experience of taking an ice bath. So you put you do it like in sports for like, say you have an ankle injury or something. You put your leg in water filled with ice cubes. It feels horrible. After you sit in it for like 5 minutes or something, you start to think like, oh, well, I'm getting used to this. This isn't so bad. But then wiggle your toes, and all of a sudden it's horrible again. And the reason is when you move that water around, it's a convection effect. Your foot has warmed up all the water in the vicinity, moved the water around, new cold water moves in and moves the energy from your foot out to other parts. So that's convection. Yeah, if you ever have to take an ice bath, stay as still as you can. Like the coach will eventually see what you're doing and come in and stir it around or whatever, but you want to stay as still as you can in there. What are we talking about?
We've done convection and convection.
Okay, yeah, so there's one more. Anyone know what the third one is? Radiation, yep. And radiation is a special one. So radiation works like so radiation is made of electromagnetic waves. It's the only one of these three that doesn't require any medium to move through. So let's say it's the only one that doesn't require an intermediate molecules. Which means that electromagnetic waves, that radiation can travel through empty space. These other two can't. And so without radiation, no energy would get to Earth from the sun, and there wouldn't be any life. I am going to talk about calculations for two of these. We'll do calculations for conduction and radiation. Convection, there's not really any way to calculate that. It just has to do with how quickly, with how little energy loss, you can move hot molecules from one place to another place. But conduction and radiation, we can do calculations for those. Okay, so conduction, think of an object like this with a, let's say it's a cross-sectional area A here, and here too. So cross-sectional area A along the, whatever it is, along the entire length L, where this is L. And let's say that the crosshatched region on this side is a higher temperature. I'll call that T1. And on the other side is a lower temperature, T2. So which way is heat going to travel? From high to low. So heat is going to travel from left to right. So the heat per time is equal to a constant, and I'll tell you what that is in a second, times that cross-sectional area, times T1 minus T2, so the difference between those two temperatures, divided by L. This K is called the thermal conductivity. A is the cross-sectional area. And think of, when you're thinking about what this A is, because like notice something difficult about doing this calculation. It's not so difficult here because I've drawn all the directions and stuff. But there are a lot of different areas you could calculate here. You could calculate this area A if I gave you this length and this height, right? Or this width and this height. But if I gave you all the dimensions, you could also calculate the area of the side that's facing us. And that would give you the wrong calculation. So how do you know that the cross-hatched area is the one that you want? Well, think of this area as, so this cross-sectional area, think of it as the window that the heat is moving through. Okay, in other words, that area is perpendicular to the to the direction that the heat is traveling. Okay, and the length, on the other hand, is the distance parallel to the direction that heat is moving. This thermal conductivity, that's different for every material. And so that's something that you have to look up. So on a test, you'll be given the value for whatever material we're dealing with. If you were ever trying to solve a problem that you came up with on your own, you could just Google that thermal conductivity of glass or something. So let me just do one quick example here, and we'll talk about radiation next time. Okay, so say you have a pane of glass. And let's say the thickness is 2 centimeters. So 0.02 meters. And let's say it's a square with lengths of 1 meter. And let's say that on the hot side of the glass, so say this is the side that's inside your house, right at the surface of the glass, it's 18 degrees Celsius. And on the other side, the temperature is 12 degrees Celsius. What's the energy loss per hour? So heat is going to travel from the 18 degrees Celsius side to the 12 degrees Celsius side. So now this is a case where we have to figure out what area we're dealing with. Which of these dimensions is going to let us calculate that cross-sectional area? The 1 meter by 1 meter. Yep. So that's, I mean, I said think of it as a window that the heat is transferring through. This is literally a window that the heat is traveling through. That area is perpendicular to the direction that heat's traveling. Heat's traveling like into the board. So the area is 1 meter by 1 meter. So what's the length? Yep. So the length is 0.02 meters. For glass, this is something I'd have to give you in the problem. The thermal conductivity is 0.84 joules per seconds, meters, degrees Celsius. And so the heat per unit time is equal to 0.84 times the area times the difference in temperature divided by 0.02. And that gives you 252, what are the units going to be on this? Joules per second, everything's in SI units, so joules per second. And what's another way of writing joules per second? Joules per second just has its own name. Watts, yep. And so now we just have to convert this from joules per second to joules per hour. So 252 joules per second, where 3,600 seconds is 1 hour. And you get 907,200 joules per hour. And so you can imagine why people go through a lot of effort to decrease the thermal conductivity of windows. And you get windows that have like layers of gas inside because like air, for example, has a smaller thermal conductivity than glass, considerably smaller. So if you have 2 panes of glass with air in the middle, it protects some of that energy, keeps it inside your house. Any questions about that? Okay.